This video is on writing equations of rational functions. So here are problems in the warm-up. We're just finding the limits as we're going to infinity or negative infinity. This one, we have the same power on the top and bottom, so we divide the leading coefficients. We end up with negative 5/3. This one, we have the power on the top is bigger. So if I plug in infinity, this is going to be infinity, negative infinity. It's going to be infinity over infinity, but this one is way bigger. So this ends up being infinity. And then for number 3, if I sub in negative infinity here, the bottom power is way bigger, so this ends up going to be 0. So these essentially represent our horizontal asymptotes. So this would be the horizontal asymptote, negative 5/3 to this rational function. This would be y equals 0. And then this one, we would have to do some math in order to find the oblique asymptote. We'd do long division, and we'd end up discovering that y equals x squared plus 1 is our oblique asymptote, and then 3x plus 2 over x squared minus 1 is our remainder. Okay, so now if we're going to graph, or if we're going to write an equation of a rational function, given a graph or given some information, we want to make sure we know the x-intercepts or roots. We want to know the y-intercept. We want to know vertical asymptote. We want to know horizontal or oblique asymptotes. We want to know holes, which we will often call removable discontinuities. And then we also need to know some other point to determine the a value of our function.
Question 1, it looks like we have an asymptote vertically at x equals 2. We have a horizontal asymptote at y equals 1, which means that the limit of this rational function as we go to infinity and negative infinity is 1. The y-intercept appears to be at 0, 1/2, and there appears to be an x-intercept at 1, 0. And I'll tell you that those are correct in this problem. The removable discontinuity does not exist in this problem. There are no holes. So as I look at this, I want to write a function, write a rational function that meets all this criteria. So if there's a root at 1, I need an x minus 1 in the numerator. If there's a vertical asymptote at 2, I need an x minus 2 in the denominator. And then the only thing that we have to figure out is, does this meet all the other criteria? And the way that we tend to do that is we put some sort of a value or multiplying value in the numerator, and then we see how it goes from here. So if I substitute in a point, for example, the y-intercept, 0, 1/2, if I substitute in 0 for x, I get a times negative 1 over negative 2 equals the y value, which is 1/2. So 1/2 equals a times 1/2, a equals 1. If a equals 1, I don't really need to write it, and everything else seems to make sense. My horizontal asymptote would still be at y equals 1, and if I take the limit of this as it goes to infinity and negative infinity, I would get 1 because the powers of the numerator and denominator are the same, and the leading coefficients, when you divide 1 divided by 1, you get 1. So the function that I want is x minus 1 over x minus 2. Let's take a look at this function. It appears that we have a vertical asymptote at 5. We have a hole, a removable discontinuity at 2, 4/9. We have no roots. The y-intercept is 0, 4/25. And it appears that the limit as we go to infinity and negative infinity of the function is 0. So therefore, there's a horizontal asymptote at y equals 0. Now, let's write some sort of function. R of x equals a times, we know there's a hole at 2, so we need x minus 2 over x minus 2. Then I have a vertical asymptote at 5, but notice that the function goes off to positive infinity in both directions. Because it goes off to positive infinity in both directions, that means that the multiplicity of that asymptote is 2. So I need to have x minus 5 squared in the denominator. So this is my function. I just need to figure out what a is. So I'm going to, for the purposes of making my calculations easier, I'm going to cancel off the x minus 2's in the numerator and denominator. So a over x minus 5 squared equals some y value. And now I'm going to substitute in points that I know. So for example, 0, 4, 25ths. So 4 over 25 equals a over, if I plug in 0, I get 5 squared, negative 5 squared, which is 25. So that means a has to equal 4. So if a equals 4, I need to make sure that everything is still accurate. So if I put 4 here, now what I look at is if I substitute in maybe one of these other points, like negative 3, am I still going to end up with 1/16? Negative 3, so that would be 4 times negative 5, which would be negative 20. And then if I put in negative 3 down here, I get 64 times negative 5, which is, well, I guess I should just cancel off the negative 5's. And 4 over 64 is 1/16. So I end up getting exactly what the points are. And if I plugged in 2, I would get nothing in this one, but if I plugged it into the simplified version, I would get 4/9. So that would tell me what the limit would be as I'm approaching that value. Okay, x equals negative 1 is a vertical asymptote, and x equals 5 is a vertical asymptote. This one has multiplicity 2. I know that I have the y-intercept at 0, 4/5. I don't have any removable discontinuities. I have a root at x equals 2, so 2, 0. And it appears that the limit as we go to infinity is 0, so my horizontal asymptote is 0. So as I look to write a function for this, r of x equals a times x minus 2. We have no removable discontinuities. And then I have x plus 1 squared x minus 5. And then my objective is to try and figure out what makes the vertical asymptote work. So if I substitute in 0, I get 4/5. So 4/5 equals a times negative 2 over 1 times negative 5. So that's 2a over 5. So a has to equal 2 in order for this to work. So a equals 2. And if I check to make sure that my asymptote still works, it does, because the power on the bottom is 3 and the power on the top is 1. Okay, number 4. Removable discontinuity. It appears there are none. I have potentially a root at 0, but I'm not so sold on that. We'll look at it in a second. The y-intercept, I'm going to actually, I'll say it's at 0, 0, because it does not appear that the point was labeled in advance, so it probably crosses at 0. It appears that we have a horizontal asymptote at negative 2. There's a vertical asymptote at what appears to be 3 and negative 3. And the horizontal oblique asymptote is at y equals negative 2. So I will write r of x equals a times x. Now what we must notice is that it does not cross the axis at 0, it bounces. So because of that, I'm going to make it x squared. And then I have x minus 3, x plus 3 in the denominator. So here are some things that I need to have. I need to have my horizontal oblique asymptote at negative 2. That automatically pretty much means a has to equal negative 2. There's no other way that I can look at this function and seem to make it work. Notice that when I am notice that when I'm looking at this function, there's no other points that I really know. So that's the only point that I know, is what happens as we go off to infinity. And so because of that, if I have x squared and then if I multiply it out, x squared on the bottom, if I put in negative 2, that's going to make this work. And so it will likely make all other points work, even the ones that we don't know where they exactly intersect everywhere. So that's my answer. Substitute negative 2 in for a, and we're good to go.
Problem 5, we appear to have a removable discontinuity at 4, but I don't think we know what the actual value of that removable discontinuity is in terms of the y value yet, so we still have to figure that out. We do know we have a y-intercept at 0, 1, and we appear to have roots at negative 2. That's a double root, or multiplicity 2, and we also have one at 3. It appears that we have some sort of oblique asymptote. So the limit as we go to infinity is infinity, and the limit as we go to negative infinity appears to be negative infinity. There is a vertical asymptote. It appears at negative 3, and there's also a vertical asymptote at 1. So we have x equals negative 3 and x equals 1. And then this oblique asymptote is something we have to find. So let's take all this information that we have. We have some sort of function, rx equals a. We don't know what the value of that is yet. I guess we should probably find it before we continue by using the y-intercept. So we have a, x plus 2 squared, x minus 3 over x plus 3, x minus 1. And then don't forget we have this whole at 4. So we have x minus 4 over x minus 4. Now, when I'm calculating everything to find the a value, I probably don't need to have these, but I'll put them in anyway. So if I substitute in 0, 1, actually, I'm not going to put it in. I'm going to make my life easier. So 0, 1. So I have 1 equals a times x plus 2 squared. Well, if I sub in 0, I get 2. If I sub in 0, I get negative 3. And I said I wasn't going to do that. If I sub in 0, I get 3. If I sub in 0, I get negative 1. So basically what happens is a ends up equaling 1/4 when you simplify all of this. So my r value is going to be, or my value for the function, my a value here, is going to be 1/4. So this is my function. And then my job is to find the horizontal or oblique asymptote. So since we know it's an oblique asymptote, I ended up writing r of x with everything multiplied out, and then I did the long division already so that this video doesn't get excessively outrageously long. And so this would be what happens when we do the long division, which means that my oblique asymptote would be 1/4 x minus 3/4. And if I look at the actual asymptote and draw it a little bit better, that's probably about where it would be. Okay, problem 6. Looks like I have vertical asymptotes at -2 and 1. And 1 appears to be a double or a multiplicity of 2. Our limits as we go to infinity are 0, so we have a horizontal asymptote at y equals 0, y-intercepts at -1. Roots, it appears that we have one root, and it is at x equals -1, and we have no removable discontinuities. So if I'm going to write this, I need to remember that this has multiplicity 2, and I can write r of x is equal to a times x plus 1 over x minus 1 squared times x plus 2. And then I know that I can use the y-intercept in order to figure out what a is. So 1 is equal to a times 1 over -1 squared times 2. So it appears that a is equal to 2 after I solve. So then I write a equals 2, and that's that. Problem 7. It appears that I can factor the numerator. So what I'm going to do is I'm going to factor the numerator. So r of x is equal to x squared and x squared. And then I have -2 minus 1, and that would multiply out to x to the 4th plus 3x squared minus 2. Then I have x squared minus 1 in the denominator. So I can actually end up canceling off that entire thing. So my function is going to mirror x squared minus 2. So if I graph this, it's going to look exactly like x squared minus 2. With some slight modifications. So it's going to look like a parabola. So what I am going to end up having to do is figure out what these modifications are. My y-intercept is at 0, 2. I have roots at plus or minus square root of 2 comma 0. And that would be clear if I factored this further into the rational numbers, or if I just set x squared minus 2 equal to 0 and solved, I'd get x squared equals 2 and take the square root with you'd get a plus or minus. The limit of both of these is infinity. The horizontal or oblique asymptote, I don't really know if this is the best way to put it, but I would say it looks like x squared minus 2, and it actually is x squared minus 2 at all points, except, so I don't know if this is the best way to put it. You may want to put none, because it actually does mirror this at every point, except for the points that are holes. So what I will notice about this is that if I factored this, I would have holes at 1 and -1. So -1, comma, -1, and 1, comma, -1 are removable discontinuities. So I would have to replace those with holes. And that would be that. Now, the last thing I want you to do is think about this problem. We're going to talk about it in class. Think about how to do it. You're given the oblique asymptote, and you're given another couple of pieces of information. You are given the roots here. So if you know this, can you figure this stuff out? And can you determine what the function value or the function is? So what would r of x be?